Hi, I'm DJ Ware. On this episode of the Cyber Gizmo, we're going to be continuing with the Linux internal series, and today, we're going to be looking at memory management right after this. So, we all know what memory does. I mean, every time we go out and buy a computer, we always look for how much memory we think we're going to need, and then we buy a machine that has that much memory in it. If we're building one, maybe we're taking the memory out of the old machine, or maybe we're adding to it, or maybe we're creating we're going to build up a new machine, and we'll need new memory for that as well. So, and again, it's the same thing. We have to take some kind of guess as to how much memory we think we're going to need over time, and then double it. That's usually what I do, but I don't know how you do things. But and that usually will last me about, I haven't upgraded this machine in probably 6 years or so. But yeah, it's got 32 gig in it. That's been plenty. And over time, even though I have gotten pretty close to that end point. But the reason for that is, we all know memory is needed by every process that runs. You have to have memory to do it. But memory in Linux is divided up into two parts. So it's not just your application that needs memory. Obviously, the OS needs some memory too. And it is subdivided so that the two the applications can't interact with OS memory. Now, OS memory can interact with application memory. But memory, there was two different types of processing that went on. There was uniprocessing systems, and you remember some things like MS-DOS, PC-DOS. Those are examples of uniprocessing systems. Multiprocessing systems are things like Unix. The DEC Alpha had, I think it was VMS, and OpenVMS, and then there was also, of course, the Berkeley systems versions of Unix as well. And, of course, Linux is also a multiprocessor. Windows NT had initially some elements of multiprocessing in it, but it wasn't quite as sophisticated until later that it actually reached a full-bore multiprocessing. So you can kind of think of NT had a lot of elements of multiprocessing, but it wasn't complete. And the first one I think that actually was Windows 2000. It was actually a full-blown multiprocessing system as defined in computer science. So if you want to leave comments below, go ahead. I'll just show you papers that indicate otherwise. Memory management is a task of the Linux kernel. And so it is a part of the kernel. And we talked about that when we were talking about the protection rings. But memory management can involve, we talk about primary being random access memory, or RAM. It's got to move data and elements of the program from disk to memory. It also has to do the opposite. It has to move things out of memory and save them someplace off onto disk in case the program is being rolled out. Maybe it's waiting on a long interrupt to complete, like a disk I/O, and the Linux kernel determines that, hey, I can steal the memory out from underneath this application, so I'll just save it out someplace, and then I'll call it back later. But there's really 5 different areas that memory management encompasses. First is relocation, and we'll talk about that in depth. That's really the meat of this presentation today. Protection, we'll kind of touch on it because we kind of already did that on the protection ring stuff. Sharing, I'm going to do in a later version, so I'll kind of give you a definition of what it does. And then I'll talk about one particular implementation of shared memory at the end. And then we'll talk about logical organizations and physical organizations of the memory just a bit to kind of tidy things up and complete the discussion. When a programmer is working on a new program or a new application, they have no clue as to where that program is going to sit in memory. Now, in the uniprocessing days, they did. Why? Because the application had to manage it all themselves. Yeah, they had to do all their own swapping and pushing data in and taking it out and managing everything themselves. So, and the program had to fit entirely in memory. You didn't have, in uniprocessing systems, in the original versions of uniprocessing systems, you didn't have a choice. It either fit or it didn't run. Now, MS-DOS played some games with that, and we'll talk about that when we get to it. They kind of dealt with that a bit. But So before the program is loaded, there's an address references that are relative to the entry point of the program. That is, the compiler, when it did its job of creating the binary, it had to determine how long. So there's three segments. There's the code segment. There's the data segment, which is used by static variables. And then there's the BSS, which is used by dynamic variables and arrays and that kind of thing. So the compiler had to make a judgment as to how much to allocate to each of those things when it built the binary onto disk. And that is the logical address space that is used when the program starts up. Linux will read that information, and then it will start allocating memory based on what it knows. And the program can then make additional requests for additional memory, or you might have dynamic libraries that are also going to request additional memory as well. We'll talk about all those. So that logical address space has to be mapped somewhere, because if I don't have it mapped to physical memory, I don't have it in my hardware. It's not actually doing anything. Logical is great for an abstraction, but it's the physical memory that matters. So, and all of that is managed at load time. Obviously, you can't do that ahead of time, because you can't just stick programs in memory just willy-nilly without any reason. They have to be running. And that mapping between the logical memory and the physical memory, that is what is known as virtual memory. So, yeah, so how does Linux determine this size? I mean, how does it know what to do here? So I'm just gonna stop this for a minute. I'm gonna drop down. Yeah, dive into the command line as always. I'm already over here, so I can. Let me just do a clear here, and we'll do size on more. And you'll notice that there's a bunch of columns here. So the first column, this one that says text. You might think that that's text in the program. No, that's the code segment of the program. So more has, and this is in bytes, this is 34K, 34,107 bytes. Data, you have, this is your static, and then this is your dynamic, your BSS data. And then this is just the total of those three in decimal. And then it also calculates the hex. The hex is used to determine the size of the program, or the total amount of memory that's going to be requested. So when more loads, when I'm actually doing, let's see, I don't know if I have any code out here. Maybe I do, maybe I don't. Oh, I have this one. I can do that one. So when I call more into memory, it's going to make a request. Yeah, let's do. Get the information back up again. So it's actually going to say I need 35,407 bytes of memory, and so Linux says, oh, I got to go allocate that. So, and that's how it knows. That's where it gets it from. So if you ever want to see the size of stuff on disk, you can do that. So let me just restart that. So why do you need virtual memory? What's that all about? Why did we do that? So if a program is accessing physical memory directly, like in the old days, there's a lot of problems with that. So the first problem is that you may not have enough physical memory in order to allocate the entire program to go in. That was a common problem that I remember when I first started programming. I worked on a machine that had 32K of memory in it. That was a mainframe. And if you wrote a program that took 33K, tough. You wouldn't be able to load it. It just would stop you and say, I can't load this. It's too big. So you had to shrink it. You had to work on that's why in the days back then, the program manuals all had the assembler in each instruction. It would tell you exactly how much assembler was needed so that you could replace one command with another to shrink it down by enough memory to get it to shoehorn in. You don't have that problem today. You don't have to worry about it. Today you just go out and buy more memory. Or you just let it run slow. But in the old days, in physical memory, you had no choice. It had to fit. Programs, when they're running in physical memory, now this was in the early days of multiprocessing, when you had programs that would run, they might be, your memory might have been allocated according to word boundaries. And so you could only allocate as much physical memory as the word boundary. You couldn't allocate less. It's whatever the word boundary was. And if that word boundary was, I don't know, let's say 16K, and you allocated 8K, you wasted 8K, right? And that left a hole. And so as time went on and things were running and going out of memory and going back in, you had all this fragmentation that was going on in memory. And if you thought you had sorry about that. So yeah, and you had to make sure that you didn't leave all these holes in memory, because if you did, eventually you wouldn't have enough contiguous blocks of memory to be able to allocate for programs that needed more memory than was left over because of the fragmentation. That was a common problem. The other one was there's no security at all. I mean, if I ran a program, I could see what you were doing. I could go and read your address space. I had free reign over the entire system. So that's not a good thing. For example, in MS-DOS, programs could see all the physical memory. And the MS-DOS application, to some degree, had to manage memory itself because the operating system, or lack thereof, it was too dumb to really do anything on its own. There was, and I don't mean that in a bad way, it just didn't have, it wasn't designed to do multiprocessing, it was designed to do uniprocessing, and so it didn't need to have a lot of logic behind it to do things. MS-DOS is, its memory management model was pretty simple until they started getting newer and newer versions of the Intel processors that opened up the address space. The original 8088, which was in the IBM PC, only had a 20-bit register, which allowed it to access up to a meg of memory. Now, I think you'll probably remember the famous Bill Gates speech that, hey, you don't need more than 640 KB. And so I think I can kind of show that. So the conventional memory in MS-DOS was 640K because Bill Gates said that's all you ever needed. The upper memory or high memory area had to be allocated special, and you had to manage that out of the application. So you had to be able to, you could access it, but not directly. You had to do some gymnastics to get it to work. As the chips evolved, as the 8286 came out, the 8386, the 8486, those had larger and larger address spaces and could address more and more memory. So there was this high memory mark, which was the 1 megabyte, and above that, you actually, in order for MS-DOS to see that memory, you had to swap it down and then work on it, and then swap it back up again, and then swap it down and swap it back up. It wasn't very efficient, and as this got higher and higher, and we got past extended, I don't remember what it was called when it got past 16 meg, but that was just a mess. It was just a train wreck. And that's about the time Microsoft started looking for a replacement for MS-DOS because they realized this wasn't going anywhere, and the Intel chips weren't going to get any smaller in their address space, and the demands for applications to do more than one task at a time was growing. I remember a couple times on MS-DOS, this is kind of off the topic, but trying to get TCP/IP to work on it. Yeah, you could do it, but it was not fun. I mean, you had to allocate those drivers way up into extended memory up here, and it wasn't very fast. And if you had a foreground process that was computational heavy, your network stopped. I was so glad that OS2 came out about that time. So, yeah, OS2 solved that. Virtual memory manages physical memory like MS-DOS did, but excuse me, if you're managing memory like the way MS-DOS did, that's called an overlay. Microsoft and MS-DOS called it paging, but that's not really correct. That's not paging. It's an overlay because it isn't smart enough to copy out what's there. It just flops over the top of it, and then it reloads the program back in from a save state. But yeah, from the high memory, it swaps it up and then back down. So the first computers, who invented virtual memory anyway? I mean, IBM did, right? No, IBM didn't. Even though they think they did, they didn't. The Atlas computer was the first to use it, and that was at the University of Manchester. They implemented a paging construct, and that was just a research device. It wasn't a commercial machine. That was released in 1962, but they had prototypes of it running way back in the 50s. Yeah, and then the first commercial implementation of virtual memory was Burroughs. they were working independently on virtual memory, and they didn't. I don't even know if they were aware that the University of Manchester was working on it. They just went off and did it themselves. Yeah, Bob Barton was a pretty smart guy, and he was one of the early ARPA researchers, and he was a research fellow for Burroughs at the time that invented the B5000. Anyway, Burroughs wanted to work. There was two methods of doing virtual memory. First is paging. Paging requires fixed size program blocks. So, and when a page is created, it's always some fixed size. Let's say, and I don't know, in those days it might have been 16K. Today it's more like about 4 meg or something like that. So those are always fixed size. We always take and try to fit as much of the program into the fixed size page, and if we need more, we allocate another page until we get it all in. Burroughs didn't want to do that because the paging segment always leads to fragmentation of memory, because if I don't completely fill the block, I'm wasting it. I just leave these holes in memory that I'm wasting. And so Burroughs wanted one that was based on segmentation, and segmentation used variable length pages. So, and the program only got what it requested. So if I needed some oddball length of memory, I got it. Exactly what I asked for. It didn't matter how many pages were created out of it. It was managed as segments. So yeah, it was a little bit better, more efficient at using memory than paging is. But they both require some mechanism because even segmentation will create holes in memory, because it will, as programs leave and come back in, you don't always get the same size applications coming back into memory. And so eventually, yeah, both methods will eventually create holes in memory that need to be dealt with. So, so paging uses fixed size, segmentation uses variable size. So yeah, so you remember the binary guys and the assembler guys from one of my videos earlier? The same thing happened when virtual memory came out. They poo-pooed it. They said, virtual memory, oh, that's going to be slow and it wastes memory. Why are you bothering with me with this? Just go away. We're fine. This physical memory thing is working great for us in our bank, allowing applications to see accounts balances, or hospitals where I can see patients' psychological profiles. And yeah, it was great. Anyway, David Sayer of IBM proved in 1969 that virtual memory ran programs at the same speed as physical memory, and he also proved that not only did it run at the same speed, it managed memory more efficiently. So then you could, in an application, the algorithms that were in the operating system were just simply better. IBM claimed that virtual memory was an invention of theirs in 1972, a full 11 years after a commercial implementation was released, and 12 years after the Atom actually had it up and running. So, yeah, good job. Anyway, they didn't invent it. No matter what anybody tells you, they didn't invent it. So how does it do this? So I'm going to look at paging because that's the method Linux uses. So how does it do this? So I have some columns here on my little chart, and I have some physical addresses here. You remember from the size, that's down from here. And then I have some logical memory addresses. This is coming from the program. This thing is a page table. This keeps track of where this code page is over here in memory. So page 0 points to 3, goes to the frame number 3 in memory. That's how you find it. It's like a lookup table. And then this is all the elements of my code in physical memory. And you can see there's some holes left here. Probably some other applications had been running. So yeah. And then you'll notice that there's also these areas down here. When I should have made this a 1, but when you have an empty one, it's marked as invalid. And the reason for that is very simply that if the program makes a request to page frame 0, when Linux goes to look that up, it's going to say, oh, that's invalid. You did a bad thing. And so, yeah, it's going to kick it right out of memory. So the other thing is that Linux stores page tables not in physical memory. They store it in the CPU cache. And obviously, there's a really good reason for that. It's speed. I want to be able to get to that table, get my data out, and get moving as fast as I can. So there's a couple of things that happen here when we're running into this. So here's my program. This is my table down here, my page number, my frame number. So I'm going to do a map of this. My CPU is starting to execute the code, and it's saying, oh, I need this code block, and it finds it here, and it goes to the frame number, and that's called a table hit. TLB is table hit, and all good. Fetches it, passes branches off the execution to that piece of code, runs it, comes back, starts on running down the program again. But what if that is not in memory? What if it just falls right down through the list, and that's a table miss? So in this case, what Linux has to do is it's got to go look at the page table and say, is this got a V or an I? Is this valid or invalid? If it's invalid, it's going to chuck the program. Now, there's a special case where it can use invalid, but in the normal case, it's invalid. Bye. You're trying to access memory you're not allowed to access. Goodbye. Get out. And if it is valid, then it will issue a request to the disk to load it. Load up this code segment. It will have allocated the memory for it already, and so it told the disk where to load it into memory. When the I/O is complete, the control passes back to this instruction, and then it goes down and finds it in the table, and off to the races we go. That's how it works. But sometimes not all pages are going to fit into memory. And this is why I have always said it's a good idea to create a swap file, is because if you get into a situation where you can't fit a program into memory, and there are some that are larger than like Maya, for example, or some of the Blender can get quite big too. But there are some programs that are going to be larger than your physical size of memory. And no matter what you do, yeah, you can go out and buy a lot of memory if you want to run them. But a lot of times all that code is going to either sit on disk or it's going to be rolling in and rolling out. And where it rolls out is to the swap. And so, yeah, you need some way to be able to handle that. And that's why you need a swap file. So in this case, what happens is that if it's not in memory, it does the same thing, it allocates an area and then brings, let's say it's looking for 5, it'll bring it, assign it to a frame number here in memory, and then updates the table, and then that's all it does. So yeah, we kind of covered this a little bit, but just in reference, it has to determine if the reference to that memory is valid or invalid. If it's invalid, it terminates the process. If it's valid, then it will allocate the free frame, issues an I/O, waits for it to complete, and then restarts the instruction. Simple as that. Memory management. These are actually part of the CPU today, but they weren't originally. The memory management units used to have to be external. You had to either buy them or they had to be written in software. Well, the ones that were written in software were pretty slow, as you could probably imagine. So the first time I ever encountered the need for hardware was on the Motorola 68020. I was loading AUX, which was Apple's version of Unix. It was actual Unix for the version of the Macintosh called the Macintosh 2. Believe it or not, the Macintosh 2 was an open platform. It had published specs, it had published standards, it was totally open. You could build boards to it, you could expand it, you could do all kinds of stuff with it. And it ran an open platform Unix. But it's kind of hard to believe, but Steve was fired by that time when this machine came out, so I don't think this would have happened if he was still there. But in order to run AUX, the original Mac 2 had a software MMU, and it wasn't able to allocate beyond what was possible to be addressed inside of the processor, which I think was 16 meg, and obviously you need more memory than that to run AUX. You needed, I think, around 32 meg, I think, if I remember right. So you needed this MMU in order to get to address more memory in the machine. And so it allowed me to access that. It also turned on the mode 32-bit, and that allowed for the structures inside of AUX to actually execute and run. So what the heck does an MMU do? Well, it's built into your processor today, so you don't need one. It's built into AMD's, built into ARM's, built into Intel's. They all have them built in now, so you don't have to worry about those. But they're responsible for handling all aspects of memory. and they're integrated into the CPU, so they run very fast, very quick. They perform the hardware memory management. They regulate the use of RAM and cache memory. Of course, that's why they have to be inside the CPU, is to be able to get visibility to the cache. And they manage Linux, make sure that there's adequate memory for objects and data structures executing at all times. So it keeps updating structures in Linux to tell it that, hey, you've got these resources available to you. Application memory management allocates the required memory that it needs. So, and those can be in two different requests. I mean, obviously you have physical and you have fixed and you have dynamic. And so, yeah, as the program allocates more memory, it's got to make a request for that. And when the program exits, when it terminates, and I say terminate, because it's either a good or bad end. I remember one time going into a customer, and I was watching it, and this program was running along, and all of a sudden it just blew up. It threw an error. And they just kept going. And I was like, wait, you just had an error. And they go, yeah, we know. That happens all the time. And I said, don't you ever want to know why that crashed like that? And they said, no, we don't care. It's fine. The program's fine. It created the data just fine. That's just the way it ends. Like, okay. Okay. So it could be a good or a bad end. That could be a successful conclusion to your program, or maybe not. Maybe, I don't know. But so how does the MMU actually work? So remember we talked about logical addresses in the program. So we looked at the size of that, and we saw that there was some code space. Let's say that I have some code space that maybe it has 16K of code in it, and I have a call that's going to address 4096. Well, the MMU is very clever. It has this thing called a relocation register, and in there is the adder for the address. And so this changes over time depending upon what is the next available memory, and then that matches this. So it's whatever has been allocated by the system, and that goes into the register. These two get added together, and that becomes the physical memory address. Done. It's that quick. I mean, it is literally just adding those two together, and you're done. That's how it maps. So it's a very efficient, a very quick, and a very fast processor to do that. So let's talk about protection just a little bit more. So processes should not be allowed to access or reference or write to memory locations unless they've been authorized to do so, unless they have permission to do that. So that protection obviously can't be done at the time you load the program. You're going to have to do that as it's running, because it's dynamic. The programs can be requesting additional memory. They can be loading additional libraries that are dynamic. And so that allocation has to be checked at runtime. So if a program attempts to access memory outside of its granted location, Linux will terminate it. Now, there is one exception to that. So if it's a dynamic library, obviously it's not in memory at the time that you start up. So there is an allowance for that. And when the code segment gets loaded in, there is a reference to that. And when Linux hits that, it will see that it's invalid, but there's a marker that says that it's a dynamic library, and it tells Linux where to go and get it. And so Linux will then issue a I/O to load that dynamic library into memory. So that's a simplification, but that's essentially what happens. Sharing, we'll talk more about shared memory and interprocess communication, but like I said, I do have one special case I'm going to talk about at the end. But that basically allows two or more processes to share the same block of memory, so that if one program is updating memory, the other one has the latest information to keep going with. And they can share, they can write back and forth to each other through there. It's a lot more efficient than sending messages back and forth and taking the overhead to do a syscall on the processor and then wait for it to give you the response back with the data that you want. So yeah, it just saves you from having to interrupt the processor all the time. So yeah, and it allows you to keep updated information between two processes. The logical organization of memory is obviously memory is allocated linearly. It starts at 0 and it ends at the top level, the top part of your memory. If you've got 32 gig of memory, that's your top address. Is one byte less than 32 gig. So the programs are organized into modules. I mean, you can have the main. Let's say you're writing a C program. You have main.c. You could have input.c, and you could have oh, I don't know, maybe some graphics routine, graphics.c. And when you compile those, you're compiling all three of those together. Even though you wrote them independently, you're compiling them together to form a binary. And in that binary, there also could be static libraries. There could be references to dynamic libraries. And all of that information is kept in the binary program that's loaded, that's written out to disk by the compiler. And in that mode, the compiler and you can assign different levels of protection to the memory blocks that you have. You can make them read-only, static. You can make them execute-only. You don't have any control over that. That's the program segments that the compiler is generating. But yeah, and you can make them read-write, of course. But the modules can be shared among processors, and we've seen that with libraries when they come into memory. You may not, just because a program is using libc, and this is one of the areas where there's a lot of problems with when you run into contention in applications that are requiring a specific version of the library. Another one calls in the library and it's a different version than the one you have. And so, yeah, Linux will kind of handle that a little bit, but sometimes that creates problems because you might have a library that's in there that's older than what your program expected, and then you may have a fault. But anyway, that's neither here nor there. But anyway, it's trying to manage and trying to be more efficient about how many copies of the library it has in memory. The code segment, of course, is read-only, and there's a command that'll help you analyze the structure. Let's jump back down again. I'll take more again and pick on that again. So the command, you probably will have to install this. I'm just going to do well, let's do an A more. This will show everything. Oh, it's not there. It's in user. Well, here we'll just tell it where it is. Okay, so first thing you'll see is that it has this magic number again, and yeah, I'm not going to talk about that. This is the ELF64. This is the class. ELF was an invention of AT&T. This was was supposed to be designed to create a singular format for executable, so that that the constructs and the structures would be the same no matter what platform you were running on. Yeah, so it didn't mean that I could run an ARM application on an x86 box, although I think that was AT&T's long-term goal before everything just fell apart. But I never got there, and to my knowledge, no one has ever finished that work to allow a singular binary. Now, Apple has their universal binaries that they use, but they're probably, them and a few others are probably the only ones that I know of that have actually done that. But you'll start to see some section headers, some addresses, and these are going to be, of course, code areas. There's the program headers, so the load areas, this is your code. You'll find some shared aspects. It just goes through. If you're looking, this probably won't mean a lot to you until you start having to look at a program dump or a trace, because it's that information that tells you where in the program things fell apart. So you can see there's your jump. There's some jumps to your libraries and what version it needs and so forth. So it's a good tool. It's a good tool to put in your toolbox. It's really very helpful at times in making sense out of a dump, especially on a program you didn't write, to kind of give you an idea of, oh, I see what part of the code this is in, and I can tell the developer, oh, this is where things went wrong. Anyway. The physical organization is the process in user space. Each process, obviously, we've said this before, needs memory to execute. And memory is partitioned between processes. We talked about this a little bit. Fixed partitioning is the code, the data segments which are static, and then you have the dynamic partitioning, which is the parts of the code which are allocated at runtime, or the libraries which are called in at runtime. The dynamic libraries. So yeah, that's the two kinds of partitions that you need. That's all I'm going to say about that. So one more thing, we should probably touch on NUMA. NUMA is non-uniform memory access is what it stands for. And Linux kernels are designed to support multiprocessing. Sometimes the hardware resources are split. They're split between physical CPUs on the motherboard. Even your desktop has multiple CPUs, but they're able to share memory through the fabric of the chip. AMD, like Threadripper, has a fabric that allows them to share memory between the processors. Intel has a fabric inside of the Core i7s, Core i9s to allow them to share, and i3s and i5s to allow them to share memory within the fabric. But this is talking about when you have like Xeon processors where you have two physical CPUs on the motherboard, each with their own block of memory. So NUMA is designed, so I can have applications running in processor 0, and I can have applications running in processor 1. And those memory locations that they're using are local memory locations, which are in the block of memory next to the processor. But what happens when the two processes need memory on? They need information out of the other process. They need to be able to access memory out of each other's box. How does that happen? So this is how it happens. NUMA. NUMA allows the processors to communicate through a bus. Now, this obviously has to be fabricated into the motherboard as well as to the chip in order for this to work. But the bus is what's used to access memory from the processors. And you have this DSM, the Distributed Shared Memory Network, which is a table that allows communication with this side of the CPU, CPU 0, CPU 1. And so, yeah, this is the thing, the structure and the mechanism by which the memory is allowed to be accessed across that bus. So that's what NUMA does. I remember that I haven't seen any of this lately, and maybe it's because I've just been away from it for too long, but I haven't been around HPCs for a while. But at one time, this was years ago, there was experimentation that was going on with NUMA in order to actually get it to work across the network. And I think they did, but I don't know whatever happened to it. Like I said, I've been out of that area for a while. So if you guys know, let me know in the comments below. So yeah, but today NUMA, NUMA is used to do this mechanism. Now UMA, or Uniform Memory Access, is really this portion of it right here, where it's accessing the common memory. But when you're trying to get memory that's owned by a different processor block, then you use NUMA to do that. I hope that you enjoyed this today. Next time we'll talk about interprocess communication a little bit. So I hope you enjoyed this, and if you did, as always, please like and subscribe. Hope to see you all again real soon. Bye for now.